think you are now being recorded.
Yeah.
Yeah, excellent, great. Thanks. Go for it.
Okay, so I'm introducing Melanie on the topic of ocean acidification and calcifiers. So, ocean acidification is mainly due to anthropogenic CO2, which anthropogenic meaning human-derived. So that's like our burning of fossil fuels and mixing of cement and things like that. Now, the pre-industrial era, CO2 in the atmosphere was rated at 280 parts per million, whereas today it's rated at around 400 parts per million, which is a drastic increase over such a short time period of only about 200 or so years. Now, the oceans have apparently absorbed almost half of the carbon dioxide that we've released since then due to burning of fossil fuels. And it absorbs it through the carbon cycle. Most of the absorption that we talk about is surface mixing. So, because of all of this, the dissolved organic carbon in the ocean is about 60 times greater today than it was before the pre-industrial, or during the pre-industrial era. So, CO2 in the water has three main end forms that I'm going to talk about. It has aqueous CO2, and then two main ionic forms of carbonate and bicarbonate. Now, when CO2 enters the water, it has a reaction with the water that forms carbonic acid. This carbonic acid is a weak acid, and therefore can release its hydrogen ions. When it releases its hydrogen ions, it can form carbonate and bicarbonate, depending. It forms carbonate and bicarbonate and release different hydrogen ions. And there's also a second reaction in which carbonate can form bicarbonate with reactions with protons. So these two reactions together show that mean that bicarbonate is the greatest concentration of ionic carbon in the water in the ocean, about 85%. So most of it is bicarbonate. In addition to this, as I said before, carbonic acid releases hydrogen ions into the water. And those hydrogen ions, the more there are, the more the pH decreases, so the % hydrogen. Now, the global average of pH in the ocean is about 8.2. And it's decreased by about 0.1 units since the pre-industrial era, which equates to about 30% increase in hydrogen ions in the water. And it's projected to increase or decrease another 0.3 to 0.4 units by the end of the century, 2100, which equates to 100 to 150% increase in the hydrogen ions in the water. So, which hasn't been seen in millions of years in such a short period of time. Now, the most affected marine organisms by this acidification are calcifiers, ones that make their carbonate shells. And that's due to the fact that the increased CO2 both decreases pH, which can lead to dissolution of their shells, and decreases the number of carbonate ions, which impedes their ability to make the shells. So, pH. This is a CO2 time series that was made around California. It just shows the change in atmospheric CO2 and pH over a long period of time, since 1955. So the y-axis corresponds to the concentration of CO2 in the atmosphere parts per million by volume, and that is the red line. And the green line corresponds to partial pressure of CO2, which is basically the dissolved CO2 it's the dissolved concentration of CO2 in the water over the equilibrium constant of it. And that's just the way we measure CO2 in the water, is with the partial pressure of CO2. And pH corresponds to the blue graph, and that's and the other y-axis. And as you can see, even though it's a small change it's still changed from about 8.1 to about 8.08 on average, which is not, doesn't seem like much, but can still have drastic effects, especially when it happens over a time of about 1990 to 2015. And as you can see, from the year they started collecting it around 1955, the atmospheric CO2 has increased from about 320 parts per million to almost 400, which is still a large increase in a short amount of time. Right, so solubility. So carbonate in the water, for our purposes, exists in 3 states, 2 of which are extremely soluble. So you have normal calcium carbonate, and then you have more soluble versions called aragonite and calcite. Now, aragonite and calcite are polymorphs of each other, which means they have the same composition but different structures, and those different structures relate to their solubility in the water. Now, at equilibrium, on average, aragonite tends to be more soluble than calcite as a whole. However, they are about equal at certain times, which I will get to. So, this graph looks a little bit confusing, but it just talks about the solubility, with the solubility being higher up here and less soluble down here. So, aragonite has a steady solubility about here, and then calcite, because of the calcium ions in calcite, they exchange with magnesium ions because they're very similar, leading to 2 main types, well, I guess 3 main types of calcite: low, intermediate, and high magnesium calcite. And the degree at which there are magnesium ions in the calcite affects the solubility of it. The less magnesium ions, the less soluble it is. So this line here corresponds to the natural magnesium calcite in the water, and corresponds to a solubility, with low solubility being at the bottom and high solubility being at the top. So aragonite, because it's not necessarily affected by the magnesium, has a steady solubility, whereas the low magnesium calcite, which is to the left of this bar, this part, is much less soluble than aragonite, with high magnesium calcite being around as soluble or even more so. So the most important ones for our purposes are high magnesium calcite and aragonite because of how soluble they are. And just to say that this y-axis log KSP it's just the equilibrium constant for solids, whereas this increases, it's proportional to the amount of product. So as this increases, the carbonate increases. Okay, so saturation horizon. So, and the saturation state. The saturation state, or this, the ohm symbol, denotes the saturation state. And that, the saturation state has to do with how much carbonate or product is being formed. And that happens at certain depths. So saturation state usually so it can be less than 1, 1, or greater than 1, and each of those has a different definition. A saturation state of less than 1 is called, leaves the water to be unsaturated, in which case there is not as much carbon ions in the water for marine organisms to use. At the saturation horizon, which is here, the saturation state equals 1, and that means that calcium carbonate is neither being dissolved nor precipitated, and that is the barrier to which, at the depth of which marine organisms, calcifiers, can no longer create their shells. So at a saturation state greater than 1 is called supersaturation, and during supersaturation, the products are formed, and it precipitates out and allows the existence of coral reefs and mollusks and stuff like that to make their shells. So this graph in particular talks about aragonite and calcite saturation horizons in respect to depth. Now, this dotted line corresponds to the aragonite carbonate saturation, whereas this dotted line is the calcite aragonite or calcite carbonate concentration. The solid line has to do with in situ, or like original, like in situ carbonate, which just means at its origin, which is not in either of those two forms. When the dotted line and the solid lines meet is where the saturation horizon is. Above the saturation horizon is where the saturation state is greater than 1, and that's at which, like above this, marine organisms can use aragonite to make their shells, but below it they can't. Now, as I said before, aragonite is more soluble at equilibrium, so it's expected, or it should be less affected by acidification than calcite, because it has shallower saturation horizon. Now, acidification actually raises the saturation horizon so that there's less of an area. It lowers the saturation state, which means that there's less of an area for marine organisms to make their shells. That. Anyone have any questions?
Before you ask for questions, let's move on to the next one and then we can